Well, I want to welcome you to what is unfortunately the very last in the 2008 series of summer lectures. We're going to go out with a bang, of course, but it's too bad that we won't be able to have some more for the rest of this summer. It's been a great season. Today we're going to hear from Arun Majumdar, and if I put on my glasses, I can actually read what I wrote about him. Arun is going to talk to us about global energy supply and demand and the consequences and opportunities that come from that topic, which could hardly be more timely, especially considering what's happened just since this series began. You all know there's no sitting in the aisles, and please do wait for the microphone during the question and answer session. If you don't do that, we're going to have to repeat the question, and that slows everything down. I'm honored to introduce Arun Majumdar, who has been the director of the Environmental Energy Technologies Division since October of last year. Dr. Majumdar earned his bachelor's degree in mechanical engineering in 1985 from the Indian Institute of Technology in Bombay, and his PhD in mechanical engineering in 1989 from UC Berkeley. He was on the faculty of Arizona State and UC Santa Barbara before joining Berkeley in 1996, where he is a professor in the College of Engineering. Dr. Majumdar serves on the editorial boards of several leading journals, directs the Berkeley Nanosciences and Nanoengineering Institute, is a member of the Nanotechnology Technical Advisory Group to the President's Council of Advisors, and is a member of DOE's Council of Materials Sciences and Engineering. He was the founding chair of the American Society of Mechanical Engineers, which is better known as ASME, Nanotechnology Institute. So you gather that he knows something about nanotechnology. His numerous awards and honors include the National Science Foundation's Young Investigator Award, ASME's Augustus Larson Memorial Award, and the Distinguished Alumni Award from the Indian Institute of Technology in Bombay. He's a fellow of ASME and the American Association for the Advancement of Science, and he's a member of the U.S. National Academy of Engineering. And it's something a little bit more personal. Much of Dr. Majumdar's research has focused on nanoscience, but there's a connection there to global energy challenges that become more apparent the closer you look. In our communications department, we've written several stories about Dr. Majumdar's research in the last couple of years. One of them was about a way you can capture lost heat using silicon nanowires in such a way that you might even have a vest that would collect your body heat and use it to power your cell phone. Another one was about converting temperature differences in organic materials directly to electricity, which might lead to cheap plastic power generators. So these are clues to some of the opportunities. I'm not sure Dr. Majumdar is going to talk about those today, but there are a lot of opportunities out there for the challenge that's presented to us. It's a pleasure to welcome Arun Majumdar.
Thanks. So when Paul asked me, thanks for the introduction. When Paul asked me to give a talk, I said, okay, sure, put me the last speaker, so that, naively thinking I'll have a lot of time to prepare. I was preparing this morning. So I was also thinking what to present, because on one side I have my scientific work, which is going on in my group and material science division, and should I, if I presented that, it'll be sort of a talk on condensed matter physics and energy, relevance, etc. On the other hand, I took over as the division director of EETD, and it's been 9 months. I've been told that there's a painful birth of something after 9 months in labor. But nevertheless, the question is which one, because sort of my life is divided now. And this sort of goes back to when I took over the division directorship. I did some talk, called up some mentors of mine, one of them in MIT, and asked her, so what should I do? Should I take up this position, or because my science is really interesting right now? It's sort of the most interesting part of my career. He said, no, just do it. He said, when do I do my science? Do it on weekends and nights. I said, okay. Went back home and said, I accepted the position, and I'm going to do my science on weekends and nights. My wife said, what about us? And, well, so I'm going to present sort of both side of it. The first, the energy of the demand side, in particular of the energy, and then I'll present my scientific side a little bit at the end, but just don't tell my wife that I'm doing all this. So, global energy, this is obviously an issue that is important to us right now, historically. This is something that I've been sort of picking up over the last, I would say, 3 or 4 years now, but more so in the recent past. And I've stolen a lot of slides, and I've acknowledged them, from various people, just to put a story together. So this is, as you can see, is the lighting pattern in the world, taken from satellite, obviously not at one time, but stitched together. But I'll come back to this picture later on. So what are the issues that we're talking today? And certainly the price of oil and price of gas is a common layman's thing, but the issues are availability of fossil fuel, energy security, certainly, economics, and of course CO2 emissions and global climate change. These three issues were there in the 1970s, and there are many experts out here who know this much better than I do. So what is it? Which one of this is most important, or is there at least 2 out of the 4 that are most important? Well, this is a slide which I find very interesting. This is the price of oil out here, and this is the availability. And the peak, the Hubbard's peak, shifts as the price goes up. All right, so here is what we've already produced in terms of billions of barrels of oil, so it's 1 trillion barrel that we already produced. This is what is available, but if your price is at $20 a barrel, well, you're sort of limited to this, but if your price goes up out here, then all of this is really available. So the availability of oil is a shifting target. But if you look at where the economies are growing, this is the oil reserves, as you know, in terms of just security of the oil reserves. You know where the oil is, the Middle East, and some in Eurasia. But this is coal. And this is Asia, Eurasia, Europe, North America. And here are the 4 biggest reserves of coal in the world, which is the United States, Russia, China, and India. And we know where the economies are growing. So if push comes to shove, if something happens out here, instability, political instability, or just turning off the spigot, we'll be turning to coal. And that, of course, has its own consequences. But any fossil fuel can essentially be turned into any other fossil fuel. The idea of turning coal to a liquid fuel has been around since World War II, Fischer-Tropsch process. So this is so the availability of fossil fuel, we have at least 150 years of coal, at least in the United States, maybe 200 years. There's debate. And so that is certainly, as far as the 3 big economies of the future, United States, China, and India, coal is certainly there. So if you're thinking about the next 50 years, the availability of fossil fuel is certainly not the issue, because there's enough. The price is an issue, and that's, of course, a question of supply, demand, et cetera. But if you turn to coal, this is the CO2 per capita, and this we all know, that the intensity, carbon intensity of coal is almost double of gasoline or liquid fuel and natural gas. So that has a CO2 implications. But perhaps the best way to look at this is the following. And I like this paper by Hofford, and there are many authors in that, which came out about 10 years ago, where it looks at the projection for the next 100 years. So this is world population, and today we have about 6.5 billion people, and here is, it's a nonlinear, it's a log curve out here, 6.5 billion people, and that is expected to saturate at around 12 billion people, 11.5, 12 billion people. And I'll show you why that is saturating. Then this is GDP per capita, which that is, if you look at how much you produce per person, that is increasing, which is a good sign. That means you're producing more. The amount of energy, this is global, not just any country or so. So the amount of energy or power that you need to produce a GDP is going down, which is also a good sign. And finally, the carbon per joule, the carbon intensity is going down, which is also a good sign. So all these 3 are good signs, except for one, that is population. And if you take the product of the first three, you'll get the total power. If you take the product of all four, you get the total carbon emission rate. And this is what it looks like. So this is the power that the world needs. Forget about the colors out here. They have implications, but let's just look at the total. Today, it's about 15 terawatts of power that the whole world needs. And it is, we are emitting at about 7 to 8 gigatons of carbon per year, and that is increasing linearly. So why is it, this linear increase is very important. Why is it increasing linearly? It's because the demand of energy is increasing, and the carbon-free or carbon-neutral cannot keep up. So that gap between what is required in terms of power and what can be supplied from carbon-free just doesn't match up. If they're growing at the same rate, you would have a constant carbon emission rate. But the gap is increasing, and this is essentially that gap. So what happens to this carbon? Well, we emit CO2, and the biggest sink of CO2 that goes out in the atmosphere are the oceans. And so I won't do any climate modeling out here, but do a very simple limiting case. And limiting case is probably the best way to do it, or at least the simplest way to do it. Let us assume, for the time being, that every molecule of CO2 that we emit can instantly come to an equilibrium with the ocean. That is, you can dissolve it in the ocean immediately. That's obviously not true. It has a lifetime of about a few hundred years or so. But let us take the best case and see how bad it is, right? Let us say it immediately comes to equilibrium, the concentration. Forget about diffusion. Diffusion doesn't exist. Let's assume that. What will happen? Well, here is the mass balance. Here's the rate of change of carbon in the atmosphere is equal to emission rate minus absorption rate. This is like bookkeeping in your bank account, right? The emission rate minus your income versus spending, and that's your, how much is there in the bank. But let us say that it comes to an equilibrium. So there is an equilibrium constant. Okay, Henry's law gives you an equilibrium constant of the carbon in the atmosphere, the carbon in the ocean, and you could write it under equilibrium. This is the best case scenario. And then you can rewrite this equation in this form. And if that's the case, you have the emission rate and some constant, all right? And that's the rate of change of carbon in the atmosphere. If this goes up linearly, this is 10 years ago. This is now a little nonlinear. But if this goes up linearly, you got a quadratic change in the carbon in the atmosphere. So essentially, just throwing it up there and it's accumulating. So this is what you get then. You get a quadratic, and it's, if today we are at 380 parts per million, you can do a little curve fitting and you can project. That's the best case scenario. That means in 50 years, we double the pre-industrial level. All right? So as we all know, that there are many things that are irreversible at that point. So the question, and this is the best case, and if you have sort of positive feedback, the permafrost melts and it throws out methane, you might be at some t raised to n, where n is greater than 2. So that's the issue that we have. And the question is, how do we turn this around? That's the big question that our whole generation and the next few generations will have to face, right? So what do we do? Well, here is the IPCC predictions or model, and this is an optimistic one, that if you were to stabilize at 550 parts per million in the atmosphere, today we are at 380 parts per million, that is the emission profile that you want. That means that this is a constant. Eventually, you want to reach a constant emission rate, which means the gap between the demand and the supply has to remain constant, all right? The carbon-free supply and the demand increase, they have to go parallel. Otherwise, you can never stabilize this. Otherwise, that'll increase. This is essentially that gap. So how do we get there? And that, of course, is, there's a lot of, today we are out here, there's some inertia in the whole economy. There's economic implications of this. And how do we turn it? This technology policy is a combination of that. And it has to be addressed both from the supply side and the demand side. It's like a stick. You want to shorten the stick. Well, if you only shorten one end, the other end might grow. You've got to attack it from both ends and see how you can reduce the demand and increase the carbon-free or carbon-neutral part of it, because if the carbon part of it grows, then you lost this battle. So both attacks have to happen simultaneously. Now there are questions, which one should we focus more? Should we do the demand side or the supply side? Well, and there are lots of economic models of it. I mean, really at the end of the day, we have to do both. Some of them will come on board in terms of actual implications at different timelines, But if you don't do both, we'll basically miss the boat because that stick might actually keep growing because we haven't addressed one side. All right? So this is a two-headed snake. So this is now, okay, so why does the demand increase? Well, this is the demand, annual primary energy demand, going in different parts of the world, North America, Latin America, Europe. This is, where are we? Out here. That's the demand out here. But look at this demand going up. Okay, this is Asia. So we have to keep this in mind that this is a global issue. You know, there's only one atmosphere. It's a global issue. And so if this demand goes up, we should be looking at that very, very carefully to see. And this, I believe, is an opportunity for the United States, especially for the commercial side, to provide technology and policy help for this part of the world to see how this could be turned down without changing a lifestyle. And that's the important part. How do we do that? So this is population is, there's a lot of data on this from the United Nations, et cetera. This is population growth rate. You can see this is Asia. It's actually going down, and it's expected to go down. This is North America. Europe is actually negative. There's negative population growth. The only reason the population of Europe actually goes up is because of immigration. It's not because actually Europeans are reproducing more. But the Africa is over here, and that is also going down. But this is based on fertility rates and implications of lifespan, et cetera. All put together, that's the population growth that you have. But there are some factoids that I think are very important to understand. Or just, you know, it's stunning what the numbers are. 47% of the population growth from now till 2050, all right? So population will grow 47%. The increase in the next 50 years will be more than twice the population of China today, all right? The less developed countries will grow 58%, developed countries will grow 2%. And the less developed countries will account for 99% of the increment in the world population. So that's, and population, as we know, is related to the energy use as well. And that depends on the income level and the GDP level. But certainly, there are two factors going on out here. And I'll come to the second factor. First is the population is going up in the developing countries. And second, the economies are improving in many cases. If the GDP, the income level goes up, the energy use goes. So we have a double whammy that is happening in the developing countries. So this is, I just want to leave you with this impression. This is the world population density in the world. So we are over here, in a sort of light to dark brown out there. This is Los Angeles, San Diego area. This is the other side. Here are the red states out here, right? It's hardly sparse. But they have 2 seats per state. 2 Senate seats per state, yeah. Nevertheless, well, let's not go there. This is Europe, United Kingdom out here. And you see along the coast, there's a lot of population. Here is Nigeria, is big pockets population. And this is the Ganges Valley in India. This is China. And this is the developing, this really highly developed region now of China, all out here. This is population density. And this is Tibet and the Himalayas. And here's Japan, high population density. So this is the population density. Now let's look at the lighting pattern. This is the lighting pattern. And you can see out here that we are over here with population density, light brown to dark brown. And certainly out here, even though there's hardly any people there are a lot of lights. And there's some pockets out here. And you can see along the coast, you can see the River Nile by the lights. It's pretty amazing. And you can see the highways going across this. But you also see China, where there was high population density, but the lights are sort of almost like out here. All right? So if you put that both together, this is what you get. If you overlay them, this is what you get. You get this a low population density highlights, high population density, and they have not yet turned on the lights. And if they turn on the lights, we have a real problem. So the question is not, we have to address this issue while addressing this issue as well. And believe me, they are really eager to looking at technology and policy help in how to move forward. So that's the real issue, that global issue that we're really facing. And as I said, you have to look at it from both the supply side and the demand side. You cannot ignore one, all right? So here is, and this is why this is important to look at the economic growth. So there's a double whammy that I mentioned. One is the population is growing, and even if you do per capita, this is primary energy per capita, and GDP per capita. If the GDP of those countries are increasing, the energy use will increase, and the population is growing. So that's the double whammy that I was mentioning earlier. And so here is all of them sort of going along almost a straight line. And you can actually know, I mean, this is China, this is India. When I was growing up in India, there were no televisions. I grew up in New Delhi at 40 degrees Celsius temperatures, okay? No air conditioning. But when people start earning more, they buy the air conditioner, they buy the flat screen TV, and they have 2 cars now. We didn't have a car. We had 2, we used public transportation. So the energy use per person sort of goes up, where the income level, the GDP of the country and the income level goes up. So you can see why they're sort of, well, we don't know exactly why they're all straight line. The United States is off the charts out here. Russia went through an interesting turn of events in the early 1990s. And that's why it sort of GDP went down and started going up now. And I don't know whether it's this way or that way. I think it's probably that way. But you have all these countries out here. So if India and China, if their GDP goes up and per capita GDP goes up, and if the population is going up, then this will really increase. And this is now the CO2 part of it. And the question that some of the countries sort of don't quite fall because France is mostly nuclear, and they sort of flatten out here. The question that we have to ask is, of course, how do we get the United States down to that level? But in addition to that, how do we want China to go that way or to go that way? I mean, that's really, and this is a chart I stole from Steve, so full acknowledgement out there. But that's really, which path do they take? And can we help them go in the right path? And believe me, there's a lot of, and I think this is one of the biggest opportunities for the green industry in the United States to provide for China and India, how to take the right path. Because we are in some ways, in many ways, ahead of the game in terms of technology and the policy side, especially in California. Okay, so as I said, we have to look at it from the supply and demand. This is the supply side, nuclear, renewables, and you can see the numbers as to where globally, where the energy, the primary energy is provided. This is millions of barrels of oil equivalent. Don't ask me to convert it to exajoules or whatever. But this is, let's just take that as relative numbers, 63, 38, coal is 43, et cetera. And this is where it goes. Industry, buildings, and transportation, roughly about 1/3, 1/3, 1/3, all right? So if you want to address this issue, well, clearly, the carbon-free or carbon-neutral side of it has to increase. And if you look at the magnitudes, it's clear that there's a huge opportunity out here. This is where Helios, EBI, JBase, CERC, and all come in, is looking at this side of it, right? And now we have to look at this side as well. How do you reduce the demand out here? And this way, energy efficiency. And this lab, of course, our division, has a long history in looking at this side and the interaction between the supply and demand, which is the grid and the utilities, et cetera. So what do? This is the United States supply. We have the primary energy, petroleum is 39%. Most of it goes into transportation. Here is natural gas. Coal is 23% of primary energy. Renewables is 1% today. Biomass is 3.3%. Most of the renewables is hydroelectric. It's 2.7%. Nuclear is about 8% or so. If you look at electricity generation, okay, so we're ignoring transportation now, electricity generation, 50% is still from coal. All right? And natural gas is about 19%, nuclear is about 20% or so. So that's where we are today. And so if you want to change the supply side, we have to look at this part and how do we increase the magnitude. There's technology, policies, all kinds of things have to happen. Wind and solar photovoltaic, solar thermal, all have to happen sort of simultaneously. And biofuels, advanced biofuels, I would say, has to happen out here. The United States has changed its fuel, and it takes about 50 years or so to change the primary use of fuel. And so it's not that this has never happened before, but we have to think for change of fuel from the supply side, it'll take about 30 to 40 or 50 years or so, right? So that's the timeline, that's a time frame that we're looking at. But what I want to focus on is on the demand side, because that's where our division, ETD, is focusing on, and the interaction between the supply and demand. Because as I said, we have to address that side in sort of almost an equal way as the supply side. And this is some history, and there's a long history out here of what happened in the 1970s. In many ways, we are reliving 1970s. And I'll tell you at the end that in some, there are a few cases that we can say that this is different. And I'll give an example. But this is US refrigerator energy use. There's a demand side of 1974 or so, and then the energy use sort of came down. And the price came down. The size actually increased. The price came down also, so energy efficiency does not mean more price if the market actually moves. And this is a combination of policy, regulation, standards, and as well as technology. So if you move the whole industry, then this can happen. The implications of that, so today we are at about 1/4 or 1/5 the energy use of refrigerator per unit refrigerator than what it used to be in the 1970s. So if the implications of that is just to compare supply and demand, here is what the energy use of refrigerators would have been if you use the 1974 standards. That's the energy use, total energy use. This is what it is today. So that's the amount of energy that you save. And just to give you a comparison, this is Three Gorges Dam. This is all of existing renewables in the United States. This is nuclear. This is conventional hydro. This is existing renewables without the conventional hydro. So and this is 50 million 2-kilowatt PV systems. So the implications are huge. So there's a lot to be gained in reducing demand by increasing energy efficiency. But energy efficiency alone is necessary, but not sufficient. I mean, we can make our home much more energy efficient, but if we buy a bigger home, you lost the battle. So it has to be reduction of demand, total demand. So how do we do that? What do we do moving forward? This was sort of 1970s, a great story, and just one example to many other such examples. So this is where the energy use in the United States is. This is 40% buildings, transportation, industry. In California, the transportation is about 40% because of the distances, et cetera. But this is roughly the thing. And the buildings are the biggest CO2 emitters. And so if you look at the demand side, we have to address buildings. Industry is a big use, and is 1/3 of the energy use. So which are the big energy hogs in the industry? Well, it is cement, steel, it is paper, glass, and all these things sort of go, at least the steel, glass, and cement go into buildings and transportation. So eventually, the big energy hogs feed into the buildings and transportation. So we have to address the buildings and transportation and look at them in an entirely different way. So how do we look at buildings? So buildings use 70% of the nation's electricity. So you're talking about coal-fired power plants giving 50% electricity. Well, 70% of that goes into buildings. So if we want to reduce CO2 emissions from coal-fired power plants, we've got to address what it's going into so that you don't have to build 5 or 10, 50 different coal-fired power plants in the future. So how do we do that? So this is what our division is looking at right now, is looking at this spread out here, the residential side and the commercial side. Right now we are focusing on the commercial, but there's some residential work also. There's residential work going on campus, and so there's a partnership going on right now. This is where the energy goes into the building. In the commercial side, it's about 26% lighting, heating and cooling. Heating, refrigeration takes about 40% of the energy. And in this side, it's about 60% of the energy in just heating and cooling, right? So what we're looking at is that if you look at this sector, can we change the way business is done, all right? Can we really impact the market and introduce some market transformation? Because that's what is needed to get there. Let me give you some numbers. So here is the famous McKinsey Global Institute study of the sort of cost of abatement, and you find the biggest chunk of that is building insulation out here, air conditioning, water heating, et cetera. And of course, they missed the big thing out there, is that when you look at that as a system, what else can you do? And they missed that, and now hopefully the next generation, which is I think coming out in the next few weeks, might have that. But that is the biggest opportunity that is the lowest of the low-hanging fruits that you can get, is to look at buildings and reduce the energy consumption in buildings. Here is where we are today in terms of sort of megajoules per meter squared per year. That's the number that we have. Here's today existing commercial buildings. And where we would be if all the buildings were built to current code, right? That's where it would be. So it's about, about 20% lower, 20 to 30% lower. Where we could be with current technology is over here, and where we need to be for net zero energy, which is where we should be going. That is, if you reduce the energy consumption in buildings by 80 to 90%, so that in the future, buildings consume 10 to 20% of today's consumption per square foot base. Then you can match it up, the rest of it, by the renewables. And essentially, you have a carbon neutral building, or you can have an impedance match between supply and demand. That's where we really need to be. So how do we get there? And it has to be a combination of technology, market, and policy. It cannot be one. If you only develop technology and the market never adopts that, it's never going to make a market transformation. So that's the combination. I'll just briefly touch upon that in the interest of time. On the technology, so we just started launching this center called HyperBreak, High Performance Buildings Research and Implementation Center. It's a multiple national labs, industrial consortium, university partnership. This is where the gaps are and the opportunities are. If you look at how widely an energy-saving measure can be deployed, so the things that can be widely deployed, sort of like changes, tightening standards, tune-up, it's like a tune-up of your car. It can be widely deployed where the energy savings are about 10 or 15 or 20% on an average. You can have deep energy cuts in zero net energy buildings, but it cannot be widely deployed because they're expensive. So how do we get the cost low enough and widely deploy is over here, looking at sort of integration and whole building approach, because building is a system. So what is that? So the way the buildings are designed today is the following. It's very sequential. You have a conceptual design, you have a detailed design, then you have construction, installation, some of it may have commissioning, then you have sort of operation, and it goes from the mechanical contractor, you have a building contractor, the electrical contractor, and it sort of goes into silos, and there's no talk, no discussion, hardly any discussion between them. And what you really want to have is this kind of a feedback loop in the building construction itself. That is, you have a conceptual design, your detailed design, construction, installation, commissioning, operation, all talking to each other and iterating. And for that, you need technology to get you there. It's like the way Boeing 777s are designed today, it's all on the computer. So that once you have everything on your computer, if you change the electrical system out here, it changes everything in the whole plane, and you can actually visualize it so that you get to know the whole impact of one change in the whole system. So if your contractor decides to put less insulation in your building, everyone else gets to know about that so that you can then choose the right HVAC system. That is not happening today. And that requires some element of technology, of course policy, but some element of technology into this. Next, you have to look at the building as a whole. You have windows and lighting, you have HVAC, you have natural ventilation, building materials where perhaps you could store energy in the future, on-site power, which can release heat, which could be used for heating the building, all talk, and thermal electrical storage, all talking to each other. Because in a real building, they all talk to each other. But what you find, the fragmentation of the industry is such that you have the HVAC companies, like Carrier, et cetera, you have the lighting companies, and they don't talk to each other. Right? They build their own products, and someone puts them together, and they don't know how they actually work. It's like saying you have driving a car, the car engine is efficient, is like 40% efficiency, the best engine in the market. You got great brakes in your car, but you're driving with your brakes on. And so the whole system, then the efficiency goes down because they're not quite integrated together. Right? That is where we are today in buildings. And so I won't go into the details. We're looking at sort of how to change the way buildings are designed and delivered. And that, of course, has to need system-level sort of models and simulations and tools. And below that has to be basic science of thermodynamics and fluid flow and heat transfer, which sort of feeds into that. Because if you change things over here, that has to sort of be reflected in in the basic science of how buildings actually interact with each other, the dynamics and sort of the time scales and the length scales of the buildings are very large. So that has to be a three-pronged effort to get into, and this is an entirely different way of designing and operating buildings. So, and that's sort of the technology side, but as I said, this is not a technology game only. This has to deal with policies because the market has to be transformed. Today, if you look at how buildings are designed, you have architects and engineers, we look at the aesthetic and the technical design, you have materials and system suppliers, HVAC, lighting, et cetera, and you have construction firms, you have a developer, you've got a property manager, you've got tenants. So any technical input and energy is given over here. But the use of energy is done over here, right? So you have a mismatch. It is a standard sort of classic principal agent problem. The HVAC, the installation of the HVAC system is decided by the developer, but the use of that is by tenant. So the tenant really has no control over this. And this person out here may not have any control of how it is used. So if you introduce energy efficiency, who's going to win? And if it is inefficient, they're pointing fingers. They say, you didn't put the insulation out there. You didn't connect it properly. So there has to be an entirely different way of handling the market side, and the policy has to change. Today, the buildings are designed according to code. That's a design performance. It is not based on measured performance. So the buildings, the LEED, gold, platinum, whatever, they're not actually measured. So you don't know how they're actually performing. So that's the first step that we have to do, is to really look at, make energy consumption visible to everyone. It's like the sort of the Prius meter that shows that the energy, how much energy, then you sort of back off and you accelerate it when you see that. Well, that needs to happen. That's sort of the first step, baby step towards changing things. The performance standards. There has to be a measurement, just like you had a refrigerator standard, there has to be a national building standard, which does not really exist in any effective way. And you can correct it for weather and climate and all that. And there has to be a price signal. If you're below the standard, you have cost of carbon. If you're above the standard, financial incentive. And then you have to have a shared benefit. If you do well, then you share the benefit. And all these policy changes have to happen. So it's a long task for all of us to do. And then, of course, what we are proposing to DOE, I'm just putting it out here, is a fully instrumented, reconfigurable, integrated whole building test facility where all these envelope structure, HVAC, lighting, windows, facade, all these things go into one. And you look at it as a system, because if you don't put all of these together and demonstrate that you can save energy, the building owners and contractors will never believe it. They say, show me. Well, here it is. And that's what a national lab ought to be doing, is to creating the home for a facility where people come together and show that this can actually be done. And this is what we are proposing, with a little bit of objection now from DOE, but we'll get there. But that's what we really need. Let me just switch to storage. We have a very strong batteries program out here. And batteries, this is primarily from the transportation side. And this is where we are today. We are, this is a specific energy or energy density in terms of range, and acceleration is specific power. And the lithium-ion batteries, the power density is certainly there. The energy density has to increase. It's sort of double or triple the value to get to where you can get plug-in hybrid vehicles, electric vehicles. And that's great. I think this has to, and there's now a strong collaboration between the ETD and Material Science Division to look at batteries in a very fundamental way, which is one of the EFRC proposals. That's great. In transportation, you worry about the density. But in residential side, if you were to use batteries in residential side, you don't have to worry about the density, because it is, what's the weight? I mean, it doesn't matter. You put it in your garage. And the power requirement for homes is much less than cars. The car's about 50 kilowatts or so. My home is on an average about 1 kilowatt, right? Hopefully it'll be less in the future. It's 1 kilowatt. So what you need is capacity so that you can do, people are talking about plug-in hybrids. You drive your car, plug into a line, and then you store grid-level storage. Well, homes are already plugged in. And that's where I think a real opportunity exists, not just in the transportation, but in the buildings as well. And so you have, and energy storage is not just batteries. We should think broadly, beyond the batteries. Batteries are certainly great. This is the discharge time of power in terms of seconds. And here's a system power rating. The batteries are over here, and obviously we want to push these boundaries, towards the larger power rating. But you can do other ways of storing energy as well. And what is the implication? What's the science and engineering of that? We should certainly keep that in mind. Let me now switch in the few minutes that are left to something that I do on my weekends and nights that my wife doesn't know. But we look at energy conversion. All right? This is the energy conversion, and this is where really Helios is. Light to fuel through this way or this way, right? That's the light to fuel. In my group, we focus on the bottom, right? And that is important as well, because 90% of the world's power is generated that way, right, today. And any increase in efficiency is useful. So this is on the supply side I'm talking about. And here is, so why don't people take fuel and directly go to electricity using fuel cells at the terawatt level? Okay, why not? This is direct. Here you pay the penalty, or you certainly burn, and from here to there you pay the penalty of Carnot limits, right? And you lose about 65 to 70% of your energy, of your fuel, okay, out there, and still you go that route. Why is it that? I mean, you're less efficient. And the reason being that it is cost effective because this is volumetric. So your power, this is volumetric in the sense you've got a combustion chamber and you've got a turbine. Your power goes as the cube of the length, the characteristic length. Whereas the material cost goes as roughly the square because it's surface. So the power to dollar ratio increases with size. So that's why you find that this route of using a volumetric approach to generating energy, this is the route to do it, right? Because if you were to use fuel cells, the amount of power is limited by your length or your surface area, which is length squared, and the dollar is roughly about that, so you don't gain at large power levels, right? So that is why people have been traditionally over the last 100, since steam engines have been going through this route. And that is unlikely to change, at least in the next 50 years. Okay, maybe something else will come up, unlikely to change. But there's a lot of gains to be made out here. And so that's on the supply side. On the demand side, heating and cooling, okay, this is 60% and it's about 30% or so. So what we are looking at is, can we change the ball game? So what I'm going to present is that potentially game-changing, not yet, but potentially game-changing in the future if we get our science and our engineering right, right? So what we have been looking at, and this has been going on for a while across the world, last 50 years or so, is looking at solid state engines and refrigerator. You take a semiconductor, put them electrically in series, you get, if you put power in and heat out, you get power out here. Or if you bias it and send a current, you can grab heat from the cold side, dump heat from the hot side, so it's a heat pump or refrigerator, depending on which side you're interested in. And so these are solid-state devices. The same device can work for both. Engine and refrigerator, the same device. You can't do that with other vapor compression ones or the steam engine Rankine cycle. And so how come people don't use it? Well, because the material of choice is an exotic material called bismuth telluride, and it's low efficiency and it's expensive. It's sort of, in all axes, it's at the wrong end. And the performance of this, so why isn't it efficient? Well, in any heat engine, you sort of compare how close are you with Carnot. Obviously, you can't beat Carnot, at least not as of today. You can't beat Carnot. So how close are you? So the fraction of Carnot is what is important. And most engines and refrigerators today, it's about 30 or 40, maybe 50% of Carnot. And the figure of merit that controls the efficiency. I'm not sure why this exclamation mark. It's not very. This is the electrical. It's a number called ZT. It's a non-dimensional grouping. This is what is called the Seebeck coefficient, or the thermal power of the material, which is how thermocouples work. And here's the electrical conductivity, the absolute temperature, and denominator is thermal conductivity. So you want to increase ZT, because if you increase ZT, the fraction of Carnot goes up, and it's monotonic. Today we are out here. We want to get to ZT of 3 or more so that you are about 30% of Carnot. So it seems like a trivial problem because each of these properties in a semiconductor can be changed by orders of magnitude. You can take a semiconductor and dope it, right? Silicon doping is very, very, very common. And you can change the electrical conductivity by 5 orders of magnitude. It's interesting that no matter, regardless of whether you can change individual properties by orders of magnitude, people have been able to change ZT by even 20 or 30%. And so that's the sort of historic, let me just get to this. This is the history of ZT out here, and this is the history out here. Bismuth telluride was discovered in 1955, where the ZT was 0.5. Remember, we had shooting for 3, and this was like 0.8 or so, and people thought, whoa, by 1980s and 90s, we'll have all solid-state refrigerants and refrigerators and engines. Of course, that did not happen. Nothing grew out here until the last few years. And that's why I said this is probably the most exciting time of my scientific life, because this is happening. It's almost like the discovery of superconductivity. Suddenly, things are going up, right? So why is that so difficult? Well, it turns out that if you change the doping level in a semiconductor, the S goes down, sigma goes up, and somewhere you get a maximum. It's almost degenerate semiconductor. And the thermal conductivity, if you increase the carrier, the doping level, there's some dependence on the carrier concentration, and this is the lattice. Again, I won't go into the details. So you cannot independently change these properties, because if you change one, the other changes. It's like this little bubble in the carpet. You press it out here, it moves somewhere else. That's the problem. And I call this the Bermuda Triangle of thermoelectrics, because we are all in it, we can't get out. It's so engaging, it draws us in, we can't get out now. But what has happened in the last few years is that people, and this is my mentor at MIT, Dresselhaus, who gave me the advice, and she predicted that if you use nanostructures, you can get to higher ZT. And it did happen, but for the wrong reasons. Not for the quantum confinement, quantum effects that she was predicting, but for thermal effects that I'll get to in a brief moment. So it's all about thermal conductivity. How do you reduce thermal conductivity in material without changing electrical conductivity? So very quickly, I won't go into the thermal conductivity in a solid is like black body radiation. The physics is almost the same. So you got black body radiation from the sun, it's coming through, and you get the solar flux, and you get sunburn. How do you reduce the solar flux is what we're talking about. And a black body Planck distribution is there, right? And what people have been doing is to make alloys. So you put a little impurity in there, and you can reduce the thermal conductivity significantly. And they call it the alloy limit. And this is where nano really comes in. You can beat limits that people thought they were limits. They're not. There's nothing kosher about those things, right? This is not first and second law of thermodynamics. These are artificial limits. So people, this is what they did. But we know from our experience, at least in the atmosphere, when you have black body radiation come in, the blue light gets scattered more than the red light. That's why the sky is blue. It's called Rayleigh scattering. The small particles, which are much smaller in the wavelength, they scatter according to, whoops, everything has got spoiled out here, the 4th power of the wavelength. So the smaller the wavelength, it can get scattered much more by the 4th power than what you would with the larger wavelengths. So think of this as the blue sky. The little alloys, atoms, which scatter these vibrations in the solid. So what we did was we just made a cloud. You put cloud cover and you reduce the flux. So if you put the particles of the right size, which is at the peak of the Planck spectrum, then you scatter everything, pretty much everything. And so you can beat the alloy limit. And so we have shown that you can actually beat oh man. I think the time is up. Someone is controlling this. All right, I'll try my best again. It was going downhill after a while. He just quit on me. If you have questions now. This is my science part of it, my policy or whatever. The global energy part is over. But I think the last thing that I'll talk about, I'm really excited about. Because, as I said, we're trying to look at things which are potentially game-changing. And the last one is on solar. And we're just starting to work. We have a patent on it. Just starting to work on it. So let me just. Yeah, I think you saw that. Now it shows up. Now it shows up. You see? We are okay now. And we can double ZT by design, which was the first sort of work which, not the first I would say, one of the first, which could increase the ZT, double the ZT by designing the materials in the right way. And that is leading to higher efficiency right now. This just came out of our lab using silicon. This is a collaboration with Peidong Yang's group, using silicon nanowires. Again, we have shown ZT of 1, which is the same with bismuth telluride, in silicon, the most abundant semiconductor. And the science is still, we don't know, because we are finding that as far as the thermal conductivity is concerned, it is behaving like an amorphous material. But it is crystalline. And there is some hypothesis that these sound waves that carry heat are being localized in some way, which no one has ever shown before. So there's some really, this goes back to, I don't know if you've heard Anderson localization. 1958, Phil Anderson showed that electrons can localize if you have disorder. And you can turn a conductor to an insulator because the waves interfere destructively locally. And that is what may be happening in the sound waves, which carry heat. And so there's some very interesting science, which if we can show, we can again beat certain limits. And that can change, that was potentially game-changing, not yet. So that is on the thermoelectric side. And hopefully the silicon thing has got a lot of interest from the VCs. They're knocking on our door because the silicon industry is right here. I mean, it's a hold off because there's a lot of work to be done. But I think this is very interesting. I'm really excited about this. Let me just last few slides on sunlight and solar thermal. There's a lot of work going on in the lab on solar photovoltaics, so solar photoelectrochemical. Elaine has been leading the effort in Helios and others. Let me talk about solar thermal because today, as of today, unless the new technology comes in, new science comes in, the price of solar photovoltaics is much more than solar thermal. So can we change the way solar thermal is done? So here is a potential way which I think could be, this is probably the first new thing that I've seen in the solar thermal area. What is it? Well, this is how solar thermal is done today. You have a collector where you have mirrors that focus onto a receiver, a heliostat, and you want to focus sunlight out here and concentrate it because you want to use the heat and go to as high a temperature as possible. It's not just the energy, it is the high temperature because the efficiency depends on how high a temperature you can reach. It's Carnot efficiency, right? So higher the better. So that's why you concentrate all the sunlight and you heat something, and it's very easy to heat. And then you run it through a Rankine cycle or like a steam engine or a steam turbine or a gas turbine, and you can produce power. And sometimes you want to store it, and you have thermal storage. This is the way it is done today. You cannot separate out this part from this because heat cannot be transmitted from Nevada to Los Angeles. You're going to lose it in between, right? And you have to collect and concentrate, which makes it costly. That's where the cost comes in, is all this collection and receiving. You've got to track all the mirrors, et cetera. This is fundamental. So if you look at now fundamentally going to the science, why is it this way and not any other way? It is because of the following, that you have a visible photon, which is coming, and that's typically around 2.5 electron volts. So the green light is 2.5 electron volt. It gets absorbed, and it's an electronic excitation initially, right? And that gets dissipated by emitting phonons of vibrations, quantum of vibrations in a solid. And that sort of decays down and produces, one photon can produce many phonons, and you sort of go down in free energy, but nevertheless you produce heat because you just increase the number of phonons and the temperature goes up. And each phonon is about 50 millielectron volt. And so you get so many phonons. But the important thing is the time scale. The emission rate is typically around a picosecond or so, anywhere from 1 to 10 picosecond, or 0.1 to 1 picosecond. So as far as this system is concerned, this is instantaneous, right? It takes about maybe 50 picosecond, big deal. It's instantaneous. What about if you change the ball game, and can you then change the system? What about if you, instead of this and then suddenly going down, if you put a barrier? Just like throwing a ball over a roof, and there's a little thing out there, so that there's a barrier which prevents it to come down immediately. And then what you have done is that if this barrier is sufficiently high, you can store it for years. And that is exactly what can be done. And this is a collaboration between Peter Volhard in chemistry and chemical sciences, Rachel Siegel, and myself. So if you could do that, then you could reduce the barrier by a catalyst and then release the energy in heat whenever you want to on demand. Okay? So that is what we are looking at right now. And the way to do that is a molecule, okay, which is an organometallic molecule, which is, you got this aromatic ring out here, either 5 or 6, doesn't matter. And you got ruthenium with, CO out here. You can basically hang pretty much anything out here. Ruthenium is now expensive, of course, but we are now looking at iron, or he's looking at iron. But the interesting thing about this molecule is that when you shine light on this, sunlight, it absorbs visible sunlight and goes through a molecular transformation, configuration change, whatever that is. It's essentially a twist of the spring, and it stays there. And it stays there, and this is a higher energy level now, where it is completely twisted, the higher energy level at about 30 kilocalories, or it's about 1.5 EV, the same units before. Now, if you expose this to a catalyst, and the catalyst is charcoal, it goes back and dissipates the heat. And so now what you could do is, instead of coming up with these, if you look at the system diagram that I showed out here, you don't have to put all these mirrors. You can put it in a pool, collect it, transport it from Nevada to Los Angeles if you want, and in the absence of sunlight, run it through a reactor, right, catalytic reactor, and get heat out. So you separated the whole process of heat, of collection. So it separates collection, storage, and heat generation, and you can store it for years. So that is what we are looking at right now. We're just launching on this right now. And as I said, if this really works out, this potentially could be game-changing, because it does this.
Arun, I'm sorry to interrupt you, but we are just about out of time. I wanted to hear the end of this story, so I didn't interrupt you before. But
I'll end the thing with funding.
Okay.
How about that? Sorry about that. Here is the fun. This is pretty dismal. Sorry to end it on this note. But here's energy funding in the 1970s, right? Energy funding has remained this. This is defense. All right? This is space. This is health increase, which is good. We're not saying it's bad. But this has to have this big climb now. Hopefully, that will happen. Let me end that on this hopefully optimistic note. So, sorry for the time. Thanks.
Thank you very much for coming. I'm afraid we're going to have to let everybody go, because there are places that a lot of our audience has to be. But I'm sure Arun will stick around for a few minutes if anybody wants to come up and ask some questions personally. Thanks for coming, and we hope to see you next year.